Okay, you've all seen the blinking lights in another video, but I wanted to show you some close-up shots. This piece of wood here is a new jack that I can put under Zoe and fold down, and it lifts the wheels up off the ground for safety. I've already had her run over me once. I've got a video about that, but I never finished it. The blinking lights are in the power section, and they sequence, and there's 10 of them, and each one of those switches are connected to one cell pack, and one cell pack holds 18650 cells. But I thought I'd do some other close-up shots. This is a front panel that's got sonar in it, and it has a secret. If I open that up, inside there is the Voom PC, which is a car computer by a company called Minibox. And this door gives me access to two USB ports, and I keep a USB drive in there, thumb drive, memory stick, whatever you want to call it, for when I'm programming, and I do backups after every programming session, and I store them on one of those thumb drives, and I rotate those thumb drives out. I have 3 of them, and I rotate them out so that if one goes bad, I still got backups on another one. And this gives me access to an LED and the ultrasonic sensor and the computer, and there is a CD drive in there somewhere. There it is. CD drive. Okay, moving around to the, well, let's cover the front some more. The wheels I got from Harbor Freight. They're chain drive. Obviously there's one on each side. It uses tank steering, where if I go in a straight line, I spin both wheels at the same speed. If I want to turn, I spin one wheel faster than the other. And the rear wheel is a caster. Okay, going around the other side, I call these ultrasonic panels because they are sonar panels, because they have the sonar and they have an LED on them, and the LED is supposed to tell me if I'm out in the field and I'm not connected to a monitor, and the ultrasonic sensor picks up something, it can light the LED and tell me why the robot isn't moving, because it sees something in this particular direction. Over here, this is another sonar panel on the left side of Zoe. This sonar panel also has a trick. It's mounted on hinges, and it's got a magnetic latch on it right there. And inside this board is a AT-Mega Arduino board. And you can tell by all those wires that it's doing something. And what it's doing is it's reading all of the signals from the sonar sensors, and it runs a little program to wait for a response and then calculate the distance to the object that's being reflected in the sonar panels. That are the only 2 secret hidden doors. Now, on this left side is, again, the wheel. One of the drive sprockets for the chain for the wheel, and a magnetic proximity sensor that's pointing on the sprocket teeth. And that indicates, gives me pulses as the sprocket turns. And so I use that to calculate odometry, although this thing has enough torque that it spins the wheels on this smooth carpet and concrete and even grass outside. The only thing I haven't seen it spin the wheels on is rough concrete on my driveway or in the street. Now this is a prototype machine, and so all the parts are marked left or right side and where they fit. See, there's even an L on that that end of that shaft for that sprocket for the left side. That's because I take this thing apart and put it back together a lot as I'm fitting new pieces. I haven't had to do that in a while, but I have a big project coming up that I'll show you in a minute. This is one of the motors. This is a motor out of a scooter. It was called a Silver Bomber scooter, and we got a really good deal on the prices on some used scooters, so I bought a bunch of those. And you can see it's got 2 wires running to it. That means it's a DC brushed motor, not a stepper motor or a synchronous motor or whatever. Let's see, under here is a panel. This is in the power section again. The aluminum section is what I call the drive section. This next section up is called the power section. There are banana jacks that connect into the plus and minus sides of the batteries when they're all connected together. And I run these wires over to a power supply that's got a regulated voltage and current adjust. And because I run everything through a big diode, I can set the power supply up to over 24 volts, and the voltage gets dropped before it gets to the batteries because it's going through a big diode. And I can charge my batteries up to the recommended 24 volts when they're fully charged and brand new. If the cells are not brand new, these are 18650 lithium ion cells. If they're not brand new, they don't charge up to 24 volts. And I got the current limited to 1.6 amps. And that's the voltage coming out of the voltage and the current coming out of the power supply. But if you look over on the power meter, it's only seeing 23.46 volts on the batteries, and that is because of the diodes that I have the power running through to prevent current from flowing in the wrong direction. Now these are the controls on the control panel. There's 3 indicator LEDs. The motor driver, the servo, and the receiver lights tell me if the that receiver light looks like it's lit, but it's not. Tell me if the radio receiver is on, and it's not because the switch is down. This switch switches between autonomous and radio control. And let's see. This switch here that's got the big guard on it is the computer mains switch. That controls power to the computer. That way I can turn the individual cells on, cell packs on, without turning the computer on until I have all the cell packs in circuit. And then this is called the control panel section. And on the very top, I have an e-stop switch, which disconnects the power from the main motor driver. The main motor driver is a Sabertooth 25 amp, and it's got an interesting little characteristic in it that that e-stop switch comes in very handy. Inside of the computer section, this section here with the sonar on it is called the computer section, and that's because inside of it is this black box, which is a Intel Atom processor CPU, and that's where all the smarts are for everything beside the Arduino board and any other sub processors. Back down to the drive section, it's got an aluminum frame, 1-inch square tubing, and these oak decorations that fit in the end of the 1-inch square tubing. I made a little jig for my milling machine and cut those on my milling machine. And that's just to class it up a little, give it more of a steampunk look, whatever. And the back wheel, there's only one. It's on a caster. And I want to put a magnetic sensor on there and a big magnet so that if the wheel turns, it can sense which way the wheel is pointing. And the reason for that is I don't have a sensor that can read if the robot is turning when I don't want it to turn. And it can do that if the wheels slip, or if it's going up a hill, or it hits a hole or a rock or something. There's no way to sense that. I want to add GPS and a magnetic compass. I have the parts. I just don't have the time to figure out how to make them work. Okay, moving up above the computer section is called the body. The body also has some switches and buttons on it. On the side, is another openable panel. I have it taped closed. It's got 4 lights on it. I call those dialogue indicators, and they tell me if the robot is talking or if the robot is listening. And the 2 other lights tell me, let's see, the first one is green. It's off right now, so you can't see it. The next one's amber, the next one's red, and the last one is blue. And the green one says it's okay to talk. The red one says it's not okay to talk because the robot's talking. The amber tells me that it's in learn mode, which means if I say something, it goes into the database. So the robot learns by listening to what I say to it. The last one is blue, and that tells me if the speech recognition software or circuit is not working, if it's sleeping. So inside the body there are, well, I'll open this up. Inside the body are I/O boards. That one drives the servos, the head servos. That's why it's up on the top there. Below that is a relay that can be controlled by an Arduino, and a 5-volt servo battery elimination circuit, which is basically just a regulator. And all the power comes in there. There's another I/O board. Well, that one I built. That one has 4 MOSFETs on it, and that's what controls the big LEDs. I got these LEDs from a place called Super Bright LEDs. These are truck markers. They are very bright. That's why when you first saw this, I had a piece of paper taped over that green one, the far left one. It's so bright that it distracts me while I'm looking at the monitor. I had to add these decorative pieces on this panel because the panel is so thin. It's really thin plastic. I had to put the screws in from the back to mount the hinges. So the big piece on the outside is basically so I could drive the hinges in there, and I made it a little decorative just because. Moving down the body further, I've got a hook for my headphones. Dragon speech recognition is designed for somebody that's standing in front of a computer or sitting in front of a computer. It doesn't have a fully directional, omnidirectional microphone. The speech recognition works a whole lot better if you're talking real close into a microphone so that it can hear your voice and nothing else. Any other sound it picks up does not help speech recognition. So that's why that is there. Zoe's sound, her voice, comes out of these 2 speakers. These have some massive magnets on the back of them, which I suspect are going to interfere with my magnetic compass if I ever put it on there. I got those speakers out of an old television set. So you can find parts all kinds of places. This circuit board down here is an amplifier. It's got a power switch and a volume control. That amplifier came out of a set of old PC speakers that I scavenged the parts out of. Cost me nothing because I save old computer parts and stuff, so free amplifier. This part of the body's got these 2 big holes in it. One of them are for ventilation. I mean, the reason that they're there is for ventilation and also to run wires through, to run wires from the body down into the computer section. And in the computer section, I have a giant power for filtering out any noise that might come from the motors. This is all power distribution stuff. There's the diode. It's a big power diode. And the reason I put those diodes in there is because my power connections are all banana jacks. You can very easily plug the black one into the red outlet and the red one into the black outlet, and bad things ensue. This is the back of one of the ultrasonic sensor boards. It's got the ultrasonic sensor behind that support, and it's got an LED. And those are all wired. The side panel, I haven't put the sensors in, and the LEDs are wired in though. What drives those LEDs? Well, that's power distribution again. This is a I/O board. Called a fidget, and she's got 2 of those. And a fidget board has 8 analog ports, 8 digital in ports, and 8 digital out ports. And the digital out ports are connected there to a circuit board that's got 8 resistors on there, current limiting resistors, and that's what drives the LEDs on the sonar boards, sonar panels. Okay, this is the right side. The right side also has the 4 dialogue indicator LEDs. Inside, boy, that's tight. Inside is another fidgets board. And the fidget board, like I said, it's got 8 input ports, 8 output ports, and 8 analog ports. The analog ports go through the cables, through that cable protector, into the head. And inside the head, they basically connect to these infrared distance sensors. So when the head swings around, I can look around the room with those distance sensors and see what's in front of the robot and on either side, and I can turn the head and look 90 degrees, backwards, whatever. The head is mounted on a pan tilt swivel mechanism. I had to recently add this plexiglass disc and those frictionless guides to keep the head from bouncing around so much as it drives. Zoe's very front panel has the infrared sensors and a webcam. And I do have software for reading the webcam, but not for identifying objects in the photo or highlighting faces or recognizing faces. So that's there for future use. The big hole there in her face is, I had another ultrasonic sensor there. It's a different kind of sensor. The thing was not trustworthy. It would work for a few minutes after being powered up, and then it just wouldn't work anymore. So I pulled it out. Again, this is her pan tilt swivel mechanism where I can move her head. She can look down, she can look up, she can turn left, she can turn right. And I bought some extra heavy servos for that and spent a little extra money on those. And again, this disc was made so that the connection to the very bottom servo was just sitting on the servo shaft, and it was kind of loose and wobbly, so I made this plexiglass disc and put it on some supports, and that keeps that thing from wobbling left or up and down, back and forth, so the head doesn't wobble as much. I got to do something for her wobble mechanism, which is actually inside of her head. That still has some problems. I need like a shock absorber or something on there to keep it from vibrating. Okay, this big open space here, I have some displays I want to put in there. They're like 5x7 LED displays. I'd like it to put text across them, like scroll it, since there's only like 8 of them will fit in there. That's another project. I've got the displays, I just haven't got the time to work on them. That's probably going to take another Arduino board. Okay, the front panel, it's got 4 push buttons, green, gold, black, and blue. And it's got 4 switches, and it's got holes for 4 LEDs. And I put them all in there. I don't know what I'm going to use them for yet. This one here, though, applies power to the head, and you can hear the servos vibrating. And this one here controls the brightness of the dialogue indicator LEDs, but it still doesn't make that green LED dim enough. I wanted those to be bright so that I could see them across the yard in the sunlight. I probably won't ever need to use them out in the dark. The underside of the head is made out of foam core. Zoe's first head, original head, I made completely out of foam core. And there are the holes for the sensors. And it was a little smaller and it was a totally different shape. And the reason I didn't go with this is because I could not get a good clean cut on that foam core and the head looked kind of trashy. But it is very lightweight and it would have made a good head. Now the inside of the head was braced with wood, and these small thin pieces of wood glued to the foam cord held interface boards for the sensors that were going to be in the head. And this round piece of wood at the bottom was where the cables exited the head, and so the wood gives it a little bit more support. But I used that head for a little while, and then I decided I wanted more. Inside Zoe's head, I have this special, highly calibrated tool. This is used to open her head and also for prying 18650 cells out of the cell holders. The nice thing about it is it's nice and sturdy, slightly flexible, and you can pry the 18650 cells out without shorting the voltage terminals. I mean, you could use a screwdriver, but you're going to end up with sparks and fire. So her head cover is removed. It's just a friction fit. Inside of her head are the interface sensors for the fidgets, the infrared sensor interface boards, and there's the infrared sensors, the back of the infrared sensors. I've currently only got 5 in there. There's an infrared sensor, there's an infrared sensor and the webcam. And I'd like to, if I have enough room in here, to put the magnetic compass and the GPS device, just because it's on the highest part of the robot. Now this piece here, I know it looks horrible, big and bulky and wood. That's the wobble. That's so that the servo can turn the head this way and that way. And that whole process, if you're looking through the camera, it really makes the picture look bad. But what that's for is to tilt the head to show that the robot is confused about something. So I have all of my cables marked, right 90, the inside is right and left. That cable is left 90 degrees. Okay, that's probably enough of the head. Okay, inside of her computer section, oh, there's a little bit better shot of the lower fidget board. The nice thing about these fidget boards is you connect them to the computer through a USB cable, And the fidget board has actually got a 6-port USB hub on it. So once I plug it into the computer, I can connect 6 other things to the USB lines. And that's important because all of the I/O boards connect by a USB cable. So that's the Arduino mounted on that side panel, that door that opens up. This white box here is a USB to HDMI converter. And I've got 2 new 15-foot cables coming out of Zoe that runs over to the monitor and the keyboard. And when she's running out in the field, she's not going to have a monitor and a keyboard. Everything's going to have to be done with verbal commands or those push buttons. That's going to be a challenge, but fun. Okay, here's the back of the mini box Voom PC. As you can see, there are a number of USB cables. I can plug in a network port. I could possibly make use of that serial mouse connection, and there's a serial connector down there, and even a parallel printer port, which you hardly ever see on computers anymore. This is an old computer. I think it's over 15 years old, but you can still buy mini box computers. And this was designed as a car computer, so it runs off of a single power supply, 12-volt power supply. So, and on this particular computer, the power supply is inside of it, so you're supposed to just be able to hook it up to a car. And car voltage, I mean, if you're just running it off battery, it's 12 volt or lower. But if you're running it off of, you know, with the alternator running, with the car engine running, it can get like 14.6 volts. So the regulation for that power supply is inside that box. There are fans in there. They're very small and they're very quiet. Other things in the computer section, there is that power diode, and it's mounted in little porcelain adapters, which are mounted in a little wooden holder, and that is to protect power going into the PC. I did actually hook up the power to the PC backwards one time, and it blew a fuse on the power supply inside of this box, the computer box, and I had to completely tear the computer apart to get to that fuse. And when I replaced the fuse, everything was fine. So I just don't want to tear that box apart again. This is just power distribution connectors. That's a big filter capacitor to keep voltage spikes that might happen from the motors, to keep them off of the computer. This over here, I bet you can't guess what this board does. This board takes whatever happens to be in the batteries, which can be anywhere between 24 volts when they're fully charged and 18 volts, which is their very lowest value, and it converts it to 12 volts. So this is to power all the 12 volt items that are in the robot, or it powers, sends 12 volts to a 5 volt regulator, and the 5 volt regulator drives the 5 volt stuff. This is a pretty hefty little DC-DC converter. I got this at Mini Box also. So it puts out the 12 volts, and it puts out really clean 12 volts. And all of the fidget I/O boards require 12 volts. So that is the main reason for that. This is the back of the front panel. And if you can see, there is a dongle in a USB connector that is wired to a switch, so I can turn the power on and off to it, which is required to reset the dongle. But I didn't want to plug it in and unplug it and plug it in and unplug it, so I put it on a switch. And that's currently not connected to this USB connector, but I can plug it into the back of the, or the bottom, oh, you can't even see it, the bottom of the fidget board, one of the ports on the, there it is, one of the ports on the fidget board, the upper fidget board, and that is for a wireless microphone for Dragon speech recognition. I bought that hoping that I could get away from the wired microphone headset that I use, but the wired microphone headset works just so much better than the wireless that I don't plug it in. I might try using it again when she's running outside. That way I could stand in one spot and let her drive around and I wouldn't have to go anywhere. Okay, this part of the back of the computer section, it butts up against the control panel, and so a lot of the wires go through there. The nice thing about this is I can pull out 2 power wires and a couple of USB cables, and the computer section comes off. It comes off from the bottom drive and power sections. And the reason for that is a lot of the goodies are in the power section below this. And one of the important things is the batteries. If you ever build a robot, you know, space is at a premium. You want to build a robot that can fit through a door, and you want to build a robot that can carry enough batteries to last for a little while, to make it fun. And so I kind of started with those dimensions, and I got really lucky with the batteries fitting in there. But the problem is you got to tear it all apart to get to the batteries. And the batteries do need to be balanced charged every once in a while. And that means you have to pull them out and plug them into a hobby servo charger with a balance port on it. And there are 60 18650 cells in there that provide the main power to Zoe. And there is another pack of cells in there that provide 24 volts, and I call those the auxiliary power batteries. I had to put those in because of this meter. This meter reads the time online, it reads the voltage, it reads the current being drawn out of the batteries, it reads watt hours, amp hours, it reads watts, it reads the temperature of the inside of the meter. Why that's important, I don't know. I wish it could read the temperature of the batteries, but there's no way to hook a remote thermistor to it. This meter requires a separate power supply, so I had to add the auxiliary batteries for it. And the power that runs to this meter is controlled by a relay that when the main power comes on, then the power is connected to this meter. So this meter is not on all the time, drawing the batteries down. However, I did run the batteries down on one time on the main batteries, and I ran them beneath. I ran the batteries beneath the recommended 3 volts per cell, and it destroyed the cells. Once you run a lithium-ion battery down too low, it becomes a paperweight. So I saw this fancy little meter here, control box. This circuit board is a low voltage detector. And so I've got that connected with the auxiliary battery pack. And this LED meter is reading the voltage that's in the auxiliary pack. And it's got jacks on there, so that banana jacks, so that I can charge the auxiliary batteries without tearing the robot apart. And there's jacks I showed you already on the other side for charging the main batteries. And this board, it's a low voltage detector, and when it gets down to 19 volts, it basically shuts off the auxiliary power to keep the batteries from being discharged and destroyed. The problem with this board is it draws a heck of a lot of power, and it actually sucks the voltage down in those batteries so fast. And my original idea was I mounted them on there, and just for coolness sake, I mounted it behind this. I made this plastic panel, and I cut a hole in my side skin on the control panel section. I cut this hole, I put this cool window on there, and it sucks the batteries down so much that I have to recharge them a lot more frequently than I thought I was going to have to. So then I just recently cut this rectangular hole in the plexiglass window so that I could access those jacks and plug it in and charge my auxiliary batteries without tearing the robot all apart. Inside of the control panel section, there's the back of that meter. There is a circuit board I made. The most important part of this circuit board is it allows connections for servos and switches and those LEDs from the front of the control panel section. And it brings all the wiring together in one spot. And the most important part on this board is the switch that switches the servo control wires from the saber-tooth motor driver between the computer, basically. No, actually it switches it between, oh, there it is. That's a Pololu servo controller board, which connects with a USB cable, and it puts out signals for two servos, two servos, and that's my left main motor and my right main motor. And it runs into this board, and then there's a double pole, double throw switch on the front that you saw. It's labeled RC and auto, and by throwing that switch, I can connect the main motor driver either to this servo controller, so the computer can control the motors, or it throws it to connect to, why is that in the way? That right there with the antenna wires sticking out is an RC servo or RC radio receiver for remote controlled airplanes. And the wires from that, there's 3 sets of servo wires. One set goes up to the board where the switch is connected, so I can switch it auto RC. And this red, white, and black wire goes up to this little blue box. And inside this little blue box is a servo connected to a lever connected to the brass plunger that connects to the e-stop switch. So, and that's connected to a standard house wiring electrical switch, because I figured if those things will handle 15 or 20 amps, that ought to be good enough for my motor driver. And that's just the back of the house wiring switch. And the nice thing about that is if the robot is on the other side of the building or outside, and for some reason it goes amok, then I can throw that e-stop switch with the remote control. It pulls in on the servo. I've got it connected to the landing gear button on the remote control, and so I can stop the robot from far away using the remote control. Okay, I did a video on this board before. Whoops. I built this board in November of 2022, I think. You'll have to look at the video, I don't remember. It's got dual power supplies on it, 12 volts and 5 volts. It's got some, that little circuit, that integrated circuit right there is actually a opto isolator to isolate things from other things that I don't want current flowing through. This is an Arduino Nano clone. Yes. And the only thing that's being used for is it's got a display that I mounted on it. There's a pot, there's a button, a push button, and the only thing that's used for is these red and blue wires. Notice one of them is labeled R, one of them is labeled L. Those come from sensors, the magnetic proximity sensors on the sprockets to detect when the wheels turn. And in my last video, I didn't show you this part. I showed you part of it. It's got 2 lines, it's got 2 readings. The pot on here controls the brightness on the display. Anyway, that is the right and left sensors, sprocket sensors. And I'm going to try and move one of the wheels and show you what it does. This is supposedly the right wheel. Okay, I turned it 9 clicks, 9 pulses on that sensor. And the numbers on the far right, I didn't show you those before, because I can do all kinds of fancy programming on this Nano board, and it's got a clock source on it. What I did was I have those right numbers. This is going to be hard. The right numbers show the speed that the wheel is turning. So you see I turned it all the way up. When I spun it, it went up to 5 and then it went back to 0. And now I've got 20 pulses on the right wheel. And then this push button actually restarts the counter in the Arduino. And I'm using the interrupts in the Arduino for, as soon as it sees a pulse, it gets an interrupt and it tallies up the points, tallies up the clicks. Now, inside the robot, you'll see a whole lot of connectors. And red and black is positive and negative. And that's the computer switch, computer count main switch, provides power to the computer. And I'm using 2 sets of terminals on each side of that switch just for current handling. And I use these pretty big hefty wires to move the current for switching the saber-tooth motor driver. There's another one of those diodes. And again, that is to protect the circuitry inside of here from a reverse connection. And that's another shot of the servo controller. There's a servo controller here in the body for the drive section, and there's a servo controller up in the body. This one is in the control panel section, and there's another servo driver up in the body for the head servos, and I think I showed you those already. Here's another shot of my little decorative pipe end caps. And those are made out of oak, and they are heavily varnished for weather protection. Not that I'm ever going to take this out in the weather. And the back wheel requires 30 pounds per square inch of air. And the front wheels take 30 pounds also. Okay, this is the underside of where the computer section sits on top of the power section. And you'll notice it's just basically sitting there. Now there's some dowel pins that hold the two together to keep them from sliding off, and keep them in alignment. This part of the power section has a switch and a pot, and that controls the power to the blinky board, and the pot controls the speed of the sequencing on the lights. Okay, this part of the drive section is open, and it's too dark in there to see anything. This is the right side drive sprocket and chain and a tire. And it's open up in front there too. I'm kind of worried about enclosing all the electronics inside of boxes, so I want more ventilation. This is the right side motor. More ventilation. And you can actually see the cells for the auxiliary power board inside there. And you can see a kind of a plastic cover right there. Those are the fuses, the main fuses, and each battery cell holder has its own fuse. So that if for some reason a cell holder shorts out and it blows the fuse, all the other cells will still be connected and be good, so they'll get isolated. And this is what my big project is going to be. This is the joint where the computer section sits on top of the power section. And like I said, it's currently being held on there with dowel pins. And the computer section can be lifted directly off of the power section, but it's very heavy. And because of the way this thing is built, the batteries are inside the power section. That kind of makes sense. And I do occasionally need to get to them to balance charge them. My next big project is to come up with a better way to mount the computer section onto the drive section. And I have an idea. I thought of drawer slides where the computer section could be locked in place with a screw or something, and then possibly slide the whole computer section forward, thus exposing the top of the batteries in the power section. But I didn't like the looks of the drawer slides. So then I found some plastic bars that are used on table saws for making table saw slides. And I figured if I mounted them to the bottom of the computer section and put some dowel pins, maybe steel dowel pins, coming out the side here of the power section, right there, then the computer section could slide onto those pins with that low friction plastic riding on the pins. And I could slide the computer section forward, get to the batteries, and then slide the computer section back again when I was done, all without having to lift it up. So I'm thinking about doing that. I bought the plastic. The problem is to get everything aligned and get everything screwed in to drill holes. I am going to have to rip Zoe apart. I'm going to have to remove her computer from the computer section so I don't drill into it. I am going to have to use an extra long drill bit for alignment purposes to drill holes in this bar here to mount the metal dowel pins. And I am really not looking forward to tearing this thing apart, because there's a chance that it don't go back together. Now, this upper section, the body, is actually connected to the computer section with wing nuts. And if you look down here, the power section is connected to the drive section with wing nuts. There's one. There's one. So this thing was made to come apart, but then as I've added more parts to it, it makes it more difficult. Oh, this is something I forgot to show you. This is the computer, and it's mounted on, wow, I built that in 2015, wow. It's mounted on this wooden platform, and the wooden platform is then on the base of the computer. And if you notice, the computer is screwed down, and there's rubber grommets in there. That's to isolate the computer, which has a hard drive in it, from vibrations coming from the chassis. However, this board that it's mounted on is mounted on foam rubber. And the foam rubber, I push on it, compresses, and that top piece is held down with those rubber O-rings, and that's more vibration isolation for the computer.